All right, so we're going to begin looking at Riemann sums. And our example of...
I got to roll them back up so they don't get stuck. Some people get hungry every once in a while. Got to keep food in.
I did just give you candy. You did just finish drinking a smoothie.
Sometimes you get hungry.
He's enjoying the little first.
All right. Riemann sums, we get Riemann sums when we add the sums of those rectangles under the curve. So that's an example of a Riemann sum. What we have here is a chart that gives the non-decreasing velocity in meters per second of a car during a 12-second time interval. Now, if that doesn't make sense with physics, I got this from somebody else, so I apologize.
Okay.
I'm not a physics expert.
This makes zero sense.
What is an upper estimate for the distance traveled in the first 2 seconds?
33.
In the first 2 seconds.
Oh, distance.
The
Distancing.
The
Zero
distance
minus
traveled.
63. Wait, is yours different than mine?
What is this?
Oh, no.
No, it's
Never mind.
no, only 62.
In the first 30.
No, because it's zero.
It's 33.
What are we talking?
Because at 0 seconds it traveled 30.
It's 33.
What is an upper estimate?
33.
60,
Wait,
isn't
what was
66?
that?
It's 90.
John says
93.
66.
Oh, yeah,
What's the
what was
question?
Because your
Oh,
initial
the
is
upper
30.
estimate?
So, but then you go up to 66.
The average
Or it's
velocity
literally
is
33
Yeah,
meters
it
per
says
second.
66.
I said
Adam
what?
says
I
66.
said 30.
Colin agrees. Okay, so an upper estimate is 66.
Wait.
And we are going meters. Okay, so 30 could be when time starts. Maybe we started time when he was already moving. And we don't know. An upper estimate could be the first second he could have been going 33 miles per hour or miles per second, whatever it is, or 33 meters per second. And then the second he's going that same velocity. So for 2 seconds at 33 meters per second, the upper limit or the upper estimate is 66. Make sense? Because it could be that at time equals 0, we are, if we were going to graph it, at time equals 0, you're already at 30. And the upper estimate, obviously he's got to get from 30 to 33, but he could be at 33 the whole 2 seconds. Okay, what would the lower estimate be?
60.
60.
But doesn't mean
Because it could be that they're going 30 for the first second to the through the second. I mean, going 30 up to the second time equals 2. Let me do it that way. It could be going 30 all the way up through time equals 2, and then it jumps to 33. All right, so the lower estimate is 60 meters. The upper estimate is 66. Okay, so now take a second, and I want you to determine the upper and lower estimates for change in position during the entire 12 seconds. All right, so I'm hearing...
Well, we only have the upper. We need more time for the lower.
You need more time for the lower? Okay, let me pause. Our upper estimate is what?
628.
And how did you do that? Karis?
Okay, well I used to do like 33 times 2 plus 38 times 2 plus 45 times 2 plus
Okay.
etc.
And the lower estimate, Noah?
I don't know. I got my lower estimate as 628. So
Okay, did you get it the way Karis did?
yes.
Okay, so if this turns out to be your upper estimate and you're starting with 2 seconds, what would you start with on your lower estimate?
0 seconds.
Well, we started with this. So for your lower estimate, you'd use those two.
Oh, okay.
So what do we get for our lower estimate? Taylor?
532.
532. Because now you're going to have 2 times 30 plus 4 times 33 plus 6 times 38. Just like we did when we did the rectangles. Remember, it depended on... yeah, you have, that's right. You have to see how many...
Do you do times 2 because... Well, the reason I
There's
did it is 'cause
2
there's, like, 2
seconds intervals.
Yeah.
And that's one thing you have to watch, because later we'll look, they'll ask you to find a Riemann sum, but the intervals may not always be the same. And that's based on time intervals. But here, each time interval, it's at 2-second intervals. All right? If you, what's the maximum possible error? If we look at D, if we have that upper limit and that lower limit, what's the maximum possible error in our estimate? How would we find the maximum possible error?
Find the average. That upper and lower. The lower O is just average.
Now, when you subtract your upper and your lower from your upper, because like, let's say we thought it was going to be, or it actually was 628, and then the error we said it could have been anywhere between 532 and 628.
Okay, so you're right. The maximum possible error is the difference between the upper and the lower. So in this case, it's what?
96.
Okay. Okay, now you could take the average to get a more accurate estimate, but that wouldn't give you your possible error.
So you just subtract them.
Mm-hmm. Because as Tim said, would you repeat what you said, Tim, about why that works?
Like, it could have actually been 628, and since we said that the lower was 532, you'd have to subtract. So because it would be there would be a 96 meter error.
Okay. Or if it's actually 532, but you said it could have been 628, there was that same amount of difference between what you guessed or the estimate and what it actually was. How could we use a lower estimate and be sure our maximum possible error is less? Okay, you could take the average, but what could we do to ensure that we have less error?
Make it 1 second interval?
You could decrease your intervals. You could do 1 second intervals, or you could do a ½ second intervals, because then you're getting a little bit more accurate at what it is. And we know that you're not just going to jump. There's no way that you can jump from 30 meters per second to 33. You can't be here and then just suddenly jump here. You've got to go through every value in between. So if you pick up more of those in-between values, you're going to be a little bit more accurate. All right? On the next section, it says, consider the region bounded by the x-axis and the function x cubed, or that's x squared plus 3 between 0 and 4. And so we want to approximate the area of this region in the following ways. The L sub 4 means you want to do a left-hand limit with 4 subintervals. This is with the rectangles like we've done before. The R sub 4 means you want to do a right-hand measurement, 4 subintervals. And M sub 4 means that you want to do a midpoint. So if we have x squared plus 3 between 0 and 4. I'm going to make this smaller and move it over. Okay, so let's say we haven't done a midpoint. Let's do a midpoint. And then you can do left and right. Okay, we know what x squared plus 4 looks like, I hope. It starts at 4. And it's going to look something like this. And we are going to estimate between 0 and 4. And we have 4 subintervals. That means if we're going to do a Riemann sum, Luke, we're going to have 4 rectangles. All right, so if we were going to do a right, our rectangle would look like this. It would be where it hits the curve. So that would be a right hand. Okay, if we do a midpoint, we are looking where it hits right there. In other words, we're going to be looking at, instead of 1, 2, 3, and 4, we're going to be measuring it at 1/2, at 3/2, 5/2, and 7/2. All right, so what is still the width of each subinterval? 1, so that's pretty easy. We know the width of each subinterval is 1. What is the height of the first rectangle?
That's supposed to be 5.
Well, we're checking it at the midpoint. This is a midpoint. Well, if the midpoint's right here, right? So it's 1/2 squared plus 4, or 1/4 plus 4. I'm just going to do this right now. Plus 3/2 squared plus 4, so 9/4 is 2 1/4. Is that right? Make sure I'm adding those right in my head. Plus 5/2, 25/4 is 6 1/4 and 4. And 7/2 would be 49/4, which would be 12 1/4 plus 4. Is that right? So, what did we get here? Somebody with a calculator real quick. Is it 37? Okay, I did something wrong then. Okay, I'll have to think about that. I want you to do left and right while I figure out what I did wrong. Okay, the original problem was plus 3. So if we subtract 4, that's what we should have gotten. All right, so you got for left what? Tim, what'd you get for the left?
26.
And for the right?
42.
Okay. So if we wanted to refine it a little bit more, we could do more subintervals. And so remember, if we do left at 8, and then right at 8, and then the midpoint at 8.
Does that average equal like your real number, or?
The average would be pretty close to that area under the curve.
Where's the middle?
Probably the middle one is going to give you the most accurate, the midpoint.
Let me see what that is.
But
The average of left to right is
33.66.
yeah, the average from left to right is going to be your midpoint. Okay, but let's think about what happens here if we add more subintervals. Well, okay, we're going to let you. Okay, so here it looks like this. So your left would start here. Now, does that look like that's going to be a little bit more accurate?
Yes.
Okay, let's think about how we could do this on the calculator. You can do the sum sequence thing or the sigma. So if we do that, let's think about how we would put it in the calculator. If we do the left at 8, okay, you've got your sum, your sequence, f of x, which is what?
Hey, I got the 42. In the dx.
X squared plus 3. What's dx this time?
0.5. Is that what we're changing it every time?
Yes, it's dx is going to be a half, right? Okay, and then you're going to have your x. For the left, we start where?
The left you start at 0.
At 0. What's the last one that we're going to end up at? Not 3. Not 4.
3.5.
3.5. And then we're moving by a half each time.
That's like my next choice.
Let me move it over a little bit. Okay, what do you get there?
59.
59?
That's what I got.
47.
What's the correct?
Okay, what did we do wrong here? No, it should be close to what we got before.
I got something wrong.
I got 29.
29 or
I got 29.5.
29.5 is right. Do you have all of this? Do I have something in wrong up here?
No, I put that in my calculator.
All right. So what would be the difference if we do right 8?
It would be the same if you started.
Okay, it would be the same, except you're going to start.
That's what. Or no, you start at 0, right?
No, we're going to start at 1/2 and go all the way to 4, and by increments of 1/2.
That would be 30.
Kelly,
How do you know which?
the midpoint's going to change with the start, right? And the end. So let's see here if we do. Okay, each rectangle is still a half, right?
Yes, should it be?
Yes. 33.25 is correct. So we have x. What did you start on, Noah?
I just think I started
On a half?
0.25 and I ended on 3.75.
Okay, you started at 0.25 and you ended on 0.75.
Yes, 3.75.
And we're increments of a half. And you got 33.25. Okay, so your calculator comes in handy. That's a whole lot quicker. If you just are doing those 4 subintervals, that's fairly easy for you to calculate. But the more these intervals you get, the easier it is to let your calculator do the work. So you kind of have to visualize what's happening so you know where to start and where to end. When we talk about the definite integral of f of x from a to b, notice the difference between the definite integral that we're looking at and what we saw as the indefinite integral is now we've got a lower and an upper limit. A is your lower limit and B is your upper limit. And the definite integral is the limit as the number of subintervals gets larger and larger and the width of those subintervals approaches 0. It's the sum of all of those areas. So that's what the definite integral stands for. Let's go to the next one. Okay, But first, what we want to do before we do that is evaluate by interpreting in terms of area. So we'll do a couple, and then we're going to talk about the rules. When we're looking at the definite integral from 0 to 2 of f of x dx, and we want to evaluate it by interpreting in terms of area, that means you're going to start at 0 and go to 2. So we're looking at this area. How could we don't have a function, how could we determine the area under the curve? It's a triangle and a rectangle, or it's a trapezoid. You could use either one, triangle or a rectangle. So what's the area of that rectangle? The area of the rectangle is 2. What's the area of the triangle?
2. Oh, wait, no. 4 over 2.
So the integral, the definite integral from 0 to 2 of this particular f of x is 4. Okay, now let's say on B we're going to go from 0 to 5. So we're going to pick up what we already have. But now this is 2, 3, 4. We're going to add this next area from 2 to 5. So we could visualize that we have another rectangle here and another triangle. What's the area of that rectangle? And the area of the triangle? So the total area is 10. Okay, now we want to go from 5 to 7. All right, so we're going to start right here and go to here. Because it's under the x-axis, it's going to be negative. All right, so from 5 to 7, we know it's going to be negative because it's under the x-axis. And what's that area? Negative 3. And if we go all the way from 0 to 9, that's to right here, we know we have 0 to 5 is 10, 5 to 7 is negative 3. What is it from 7 to 9? Negative 5?
Yes.
We could do another triangle, or you could do the trapezoid, which is half the sum of the bases times the height. Here the height's 2. This base is 2. 2 plus 3 is 5 times 2, so negative 5 is right. So this is 2. Okay, we're good. All right, we're doing okay. So if we were going to do, and this will be part of your homework, if we were going to do this, from 1 to 3, 1 plus 2x, what would be your first, if we're going to evaluate it in terms of areas, what would be your first thing to do on number A and B? What would you have to do? Graph them. So we would graph them, and then we could determine the area. So we want to look at some properties of definite integrals. And we can, some of these we can think about in terms of area. The definite integral from a to b of a constant times dx. If we just have a constant, and we were to graph a constant function, it's going to be a horizontal line, right? Okay, so we'll say that this is c. So y equals c would be that constant function. And let's say we're going to go from A to B. How would you find the area under the curve from A to B? What kind of figure do I have, Colleen?
Rectangle.
A rectangle. How do we find the area of a rectangle?
Length times width.
What are our base times height? In this case, what's my height?
Your height is C.
And what's the base?
B minus A.
Which gives us that property. So we can visually see why that's the case. Okay. Another property of a definite integral is if you have from A to B of a constant times a function, you can move that constant out to the front. Sometimes that's easier to evaluate if you do that. Okay, so if you were going to evaluate, say from 0 to 1, 2x dx, it might be easier to do twice x dx and just graph x instead of graphing 2x. Then whatever you get, you can multiply by 2. All right, the third one says that if you have two separate functions that you're adding together or subtracting, you can write them as two different integrals, just like with the indefinite integral. Make it a little bit easier to calculate. The fourth one says that if you're going from A to C of f of x dx and then from A to B, that's the same as going all the way from A to B. Notice this number has to match this number. If we think about it, so here's A, here's C, and here's B. If we go from A to C and then from C to B, that's the same as going from A to B. Or if I change the order even, let's say we've got B, A, and C. If I go from A to C and then from C to B, that's the same as if I went from A to B. I end up at the same place. Guys, y'all need to stand up? Luke? And I know some of you all, it's not because you're tired from working out. Okay, and then one that's not on here that I want to talk about.
That is just me.
What?
Wow.
What? Not the only one here, what?
Oh, okay. No, what? I thought that was
Usually I
next
can use
step.
an excuse.
Okay.
I thought she was.
So what I'm going to add is if you go from A to B of f of x, x. Well, at least A to B of f of x dx is the same as the opposite of B to A, f of x dx. Okay, right now these are all properties that we're going to be using in connection with area under the curve, but they're going to translate when we actually begin to find some Riemann or some definite integrals of other functions where it wouldn't be so easy for us to find the area under the curve. All right, if we go to the next, and we're asked to compute the following definite integrals using what we've presented so far, you're going to graph those and find those areas. Okay, that's part of your assignment. You have the number 2 from before, 2a and b that was on the previous page. These 5. We're not going to worry about the trapezoidal rule right now. It's another way that you can find area under a curve that we'll look at later. It's not considered a Riemann sum because it's not in rectangles. And on number 5, this is also part of your assignment, except you do not have to do the trapezoidal sum. So, what do you think you're going to do on 1A?
Just number 1.
Just number 1. So how are you going to do that?
A lot of calculations.
On a lot of calculations.
So are we not doing B?
I'm going to take the calculator.
You're going to take the calculator and let the calculator do the computation, but you've got to figure out what to put into the calculator. Where do you start it? Where do you end it? So remember that dx is b minus a over the number of subintervals. End point minus start point over the number of subintervals. That's how you find your dx. That's how wide each subinterval is going to be. All right. You can do number 2. The rest of these you should be able to do. Okay, so that's your assignment.
So we're doing 1 through 4 also on the back?
1 through 4 on the back.